Welcome to Statistic Learning Session. Today, I'll be talking about Wall's test for implicit hypothesis. In last session, we derived the expression with the theta here in the last expression. So what we're going to say today is that we cannot put theta here. We cannot put a theta here. That's what we're going to say. Because, because under null hypothesis, we don't know what actual theta is. Therefore, we cannot say that under null hypothesis, we cannot say that theta is theta naught, and because we don't know what actual theta is. Therefore, as a estimator, we'll use theta hat as an estimator that will allow us to write this expression such that where gamma of theta hat scaled by square root of n multiplied by g of theta hat minus g of theta is asymptotically standard normal. Asymptotically standard normal. That's what we're going to say here. Because of this Slutsky's theorem, if the gamma of theta is continuous on theta. Is that clear? Do you have any questions? All right. So then, under null hypothesis, as we know that g of theta is equal to 0. Therefore, what we can say is that this expression Tn, test statistics expression Tn, is of this, where it is of square norm. It is a square norm that converges to chi-square. Why it is square norm? Because you see here, there is a one g1 here, and there is a one g2 here. Correct? And then this is a one expression. And because of this becomes a square norm. As a result, this becomes a chi-square distribution. Now, we need to, based upon this test statistics, we need to write a test. And what is this test? The test says that since this is chi-square, we need to reject if test statistics Tn is larger than something. And what would that be? It should be Q alpha of quantile of chi-square distribution with k degree of freedom. Q alpha, where Q alpha is 1 minus alpha quantile of chi-square distribution. And for this, understand the value of this, we need to look at the table. Having this kind of, well, just recap what we learned today. We learned about Slutsky's theorem and how you can apply Slutsky's theorem to the expression we derived earlier. This is the expression we derived earlier in our last session. And we applied Slutsky's theorem depending upon if gamma is continuous on theta. And then we can say that gamma of theta hat, we can replace gamma with theta with the theta hat, theta with theta hat, such that it is asymptotically normal to standard normal. Then we can say that under null hypothesis, this becomes a This expression, the square norm of this becomes a chi-square distribution, and the square norm of this becomes a chi-square distribution, and as a result, we can this is square norm, all right? This is square norm, and we can say that this test statistics Tn, we can reject the Tn if it is greater than Q alpha. This is and one last thought. This is different than the Wallace test only because in Wallace test we know that theta is equal to theta naught, but under here in our case we don't know what theta is theta naught. That's the only difference. And except this, everything is same as a Wallace test. That's all for today. I'll see you in next learning session. Thank you so much.